Gradient clipping is the common way to address exploding gradients. So if you remember, exploding gradients come about when you've got either large weights in a network or large derivatives in a network that cause the calculation of the gradient to get extremely large. Right? As the gradient gets extremely large, then as you apply that, you normally get some sort of a positive feedback loop where the gradient gets larger and larger and larger and larger over the steps until eventually it usually overflows. The standard approach to dealing with gradient clipping is something like this. So let's say that your gradient with respect to some particular theta. So this is a vector, right? We've got some sort of values here, and let's say we've got some very large value. Well, one thing we can do is clip it. So we can just say we're going to have some maximum bound k. And we're going to ensure that none of the values in here are going to be greater than k. So what we'll do is we'll just go ahead and clip partial L partial theta with k. That is, any values larger than k will get set to k. So it's not unlike a ReLU. So the clipping is really, I guess what we would say is a max here. Right? That's what the clip actually is. So what would happen then is these would pointwise get reduced to k. So large ones would get reduced to k, smaller ones would get left at their values. So that would ensure none of the individual values in this gradient vector are larger than k. And our hope then is that we'll remove this positive feedback loop. That works. That's called value clipping. So we just do some pointwise max of the tensor that is the gradient. However, there is one disadvantage to this. That is, let's say we're in the two-dimensional space. Okay? So we've got a vertical component of our gradient that looks like that, and a much larger horizontal component. Okay? So there's a vertical component, this is a horizontal component, and we decide we want to clip this. So we clip, let's say, to here. Right? So then what happens is our new vector is something like this. However, if we consider our original vector, right, our original vector went to here, if we do sort of a vector arithmetic. Its slope was that. Our new value is going to have a different slope, right? The big looking, rise over run, we've got a rise that stays the same, but the run is less. So we're going to have a higher slope here than we do here. So that means our gradient is actually going in a different direction than it originally was. So an alternate form of clipping is called norm clipping. So here, in the value clipping, the direction may change. Norm clipping ensures that the direction does not change. So if it is going to reduce, let's say, this component by a third, it's also going to reduce this component by a third. So we would actually end up with a vector that looks like this in the vertical component. And all we really do for norm clipping is do something like this. We take our gradient and we divide by the gradient's magnitude. Okay? So we just take the magnitude of it and divide, and now we've got a unit length vector here, which is the gradient. Okay? So we have maintained our direction, we have just shrunk the length of it. Okay, so it'd be as if we took this one here and just shrunk it to here. So we're reducing both this component as well as this component. And normally, of course, we have a lot more components, and so we're reducing them all. So this will now be a unit vector, and now we can multiply by our maximum vector length of k. So the idea is we would only do this if the length of the vector is greater than k. So if this length is greater than k, then we go ahead and apply this transformation. Otherwise, we just go ahead and leave the gradient alone. So if the length is longer than k, this reduces it to k and reduces all of the elements proportionally. So these are the two kinds of clipping, norm clipping and value clipping. And these are the approaches that are used to avoid exploding gradients. We'll see that vanishing gradients remain a problem. As we talk about CNN architectures, we'll see some approaches to dealing with that.